Am I audible in the back? Is it better now? Audible? Okay. So what were we doing in the last class? Address decoding. Yes. उससे पहले sense amplifier के बाद sense amplifier we had done in the previous class.
Negative bitline, right assist circuit.
We looked at the right driver. Sense amplifier, we have already looked across 2 lectures. And in that, we identified that there are 5 stages of operation of a sense amplifier. And then we had moved to the right driver. And we saw that there was just some very basic circuit of right driver that we had thought of when we talked of the 14 transistor D-latch conversion to a 60 memory cell. That point of time, we said we will put one NMOS in the bottom, and that is our right driver. But that we also realized was very insufficient and very incapable of handling the challenges that we have to handle at the compiler level. The first and foremost thing, what was the biggest challenge there? When we have a negative bitline right driver and you have to design for a compiler, what is the biggest challenge?
Separate instances. So for lesser rows, we might go beyond the negative.
So what we did see was that depending on how many rows there are in an instance, if you have a capacitance that would couple charge onto it, then for very small instances where the bitline capacitance is small, a lot of charge would be coupled on the bitline. And the bitline would go to a voltage level which is far below the safe limit for that particular technology. So we decided that, we realized that it is not easy to design a negative bitline right driver. And to be able to do that, we need to take an extra step. And we talked of something that we called as a replica bitline, which would emulate the behavior of the actual bitline. And when the replica bitline has discharged or something has happened on the replica bitline at a desired level, we would trigger the negative bitline activation circuitry. So what happens? For very small instances, this negative bitline ka replica, the one that we created, will respond faster than for large instances, where this will respond slower. And as a consequence, you will trigger the charge onto the bitline capacitance much early in a small instance. And much later, almost when my bitline has been discharged to 0 in a large instance. How does this benefit us? How does triggering the negative bitline circuit earlier or later benefit us? Yeah, we are doing this for the reliability, but how does this ensure reliability?
It ensures that the voltage level does not go like too negative beyond.
How? That is what is reliability. How does it ensure that?
So because if we have a bitline, suppose if we have a larger array, so the capacitance of the bitlines will be higher. So the slope at which the voltage decreases will be less conservative, flat and slow. And if we trigger it, then if we trigger those negative bitlines later, even then we'll be able to reach at particular negative voltage. But if we have a higher slope, then we trigger at the same time, then the negative voltage that will reach will be much more the negative direction, so that can cause.
See, time is a different thing. Time is an element of when why trigger. What I'm saying is, how does that prevent a reliability issue? I triggered it earlier for a small row instance. I'm saying now no reliability issue. If I would have triggered it later, there would have been a reliability issue. How is time related to reliability? Reliability, we understood, is related to the voltage at which my bit line would go. How is time related to that? We created a replica line and we said this would work like that. How is it related? Mhm. If we trigger late, then we can boost for a longer time. What do you mean by boost for a longer time? We only have a a capacitor, which would transfer some charge onto the bitline capacitance. It will take whatever time it takes. How does the time of my triggering change the duration of the charge transfer? Yes, if the bitline is short, we want to trigger it earlier. Why? How does it help? Why we know to ensure reliability, but how does triggering it earlier help? That negative charge is going to be equal. Whether I have a small instance or a large instance, whether I trigger it early or whether I trigger it later, the negative charge that I'm transferring onto the bitline is going to be the same. How does triggering early help?
Trigger it earlier. So if you're charging, if you're transferring the equivalent amount of charge, triggering earlier means that it will be at that point it will be at a higher voltage bit lines.
Mhm.
So when we do same thing is what we less than negative.
So look at it like this. You can't look at it. Let us say this is my tank. A tank is like a capacitor which is storing some charge on it. This is the tank of my negative bitline right driver. Okay. It can sink and it will sink as much charge, let us say. And let us say there is another tank and another tank over here. Are you able to see this? I'm talking about one large capacitance. Large capacitance means a very large capacity tank, which is 1024 rows equivalent, and one very small capacity tank, which is 4 rows equivalent, and a fixed tank of negative bit line. When I trigger the negative bit line circuit for a small capacitance earlier, what I'm essentially doing is I have not yet emptied this tank. This tank is still having some charge on it. And when I turn this on, this charge also goes here, and my total negative bit line is maintained within, let us say, minus 100 millivolts or minus 200 millivolts, whatever was my specification. For this larger tank, I triggered it much later, almost when there was nothing in there. So that when this negative charge comes, it, it again takes my bigger tank now to a similar negative voltage. My time of trigger has to be determined by how much charge I still have on my bit line. and the size of the bit line. If the size of the bit line is large, I want much lesser charge on the bit line. If the size of my tank is small, I would rather have a higher level of charge there, and that is why I will trigger it much earlier. Are you able to see this? Time, there is no other magic that is happening here. I started to discharge the bit line, and even before it had completely discharged, I triggered the negative bit line. That ensures that my bit line itself had some charge to prevent it from going to very low voltage level. Are you able to see this? Clear? Any questions? So see, over here, we're talking about a systematic variation that is being imposed on the right driver by the virtue of that right driver being used in a memory compiler. If it was just one memory, I could tune the arrival time of the negative charge for just one place. But now, because there is a wide variation, what I also do is I create another tank, which I call as replica tank, replica bit line. And I observe what is the level of charge in this replica. This replica is used to track, for this particular instance, it will track this, and for this particular instance, it will track this. That is why it is called a replica. So if it has to track the actual bit line or the actual tank, do you realize that it has to be created in almost the same manner as a real bit line? It will consume similar kind of area. It will consume similar kind of uh, right driver or something, or double the area and double the right driver, whatever. But in some ratioed manner, it has to track the real bit line for that particular instance. We'll discuss more about replicas very soon after we close mismatch and start with design verification. Uh, but keep this thing in mind. In memories, replicas are used very often so that we are able to achieve the configurability that we need inside the memory circuits. Is that okay? So after that, what did we do? Any question on the right driver? Okay. Yeah.
If we have a larger capacitance, then because what we essentially want is that we will have a certain charge on the bit lines, and when we provide a negative charge, that charge will go to a certain negative value.
The voltage of the bit line will go to a negative level.
So in that case, if you have a higher capacitance, so it will require lesser voltage to configure for that particular charge that you wanted. And then
Don't get confused. Always apply the principle of conservation of charge. There are two capacitors, okay? Let us say this is the capacitor for the right driver. This is the capacitor for your bit line. And over here, you had a voltage source. This voltage source, when the switch was closed, would discharge the CBL. There is another replica that I have, which is a similar voltage source, and it will track. That's a different thing. It will discharge the CBL. If I allow it to discharge for a longer time, the CBL will almost reach a voltage level of 0. If I do not allow it to discharge for the entire time, this voltage level will remain at, let us say, 0.6 volts. So when I say this volt, let us say this capacitance is 1 femtofarad. Just for some funny calculations, okay? 1 femtofarad नहीं 1 picofarad कहा जाता है, bitline, okay? So what is the total charge that I have on the capacitance on the bitline? In the first case, it is 0. In the second case, it is 0.6 into 1 puff. So 0.6 picocoulombs. Are you with me? Now I am saying that this CWD can put in a capacitor, and this CWD have a capacitance of, let us say, uh, 0.2 puff. Let us say. Now at 0.2 puff, I take it to minus VDD. So minus 1.2 volts. What am I talking about? Minus 0.24 picocoulombs. Is this clear? When I connect the negative bit line capacitance, I remove this. So first I remove this, then I connect these two capacitances together. What happens? In the first case, this is the total charge on my capacitance combination. So my total capacitance is 1.2 picofarads, and the total charge is minus 0.24 picocoulombs, which will lead to minus 0.2 volts. Are you with me? Now let us say this capacitance was smaller. Let us say this was 0.2 or 0.4 picofarads, much smaller. Okay. In that case, if I had taken this to 0, what would be the final voltage? Minus 0.24 upon 0.6. Are you with me? This is a risky voltage. This would lead to breakdown. What do? We say that for the smaller capacitance case, I will trigger it at a higher voltage. So what is the charge on my initial capacitance then? Something like 0.24. What is the charge on this? In this case, I have triggered it a little early. So my output will be only at 0 volts. If I were to instead trigger it at, let us say, 0.4, then my charge would be around 125 millivolts, minus 125 millivolts. So do you realize that if I change the point at which I trigger my word line assist, I also change the negative voltage that will appear at the bit line. Are you able to see that? I am only applying the principle of conservation of charge. That's the most foundational principle that was taught to you first year. I'm not doing anything else. Are you with me? Is the confusion handled? Sorry? The summary of that is whatever comes, follow the principle of conservation of charge. I calculated the charge on the first capacitor, I calculated the charge on the second capacitor, and I said those once I short the two capacitors, the charge will remain conserved. So I added the charge and I divided by the total final capacitance. The two capacitors are in parallel. So I simply divide by the total capacitance. I will get the voltage at the combined capacitance later. Is that clear? Is it okay? Okay. Okay, you tell me if अभी हमने यहाँ पे example देखा when I had kept the bitline charged to 0.6. Even after putting the negative word line driver, my final capacitance, my final voltage was coming to be zero. Was it not? That was what we saw. What that means is that if I trigger my negative word line drive, my negative right driver earlier than what my bitline needs, I will not be able to get the desired negative voltage on the bitline. So if the bitline capacitance already has a lot of positive charge on it, then whatever negative charge you will throw from the right driver will not be sufficient to take it down to the level that you want to take it down to. Is that clear? So after that, we looked at the address decoding and its impact on the scrambling of memory. What is memory scrambling?
The connection of the logical addresses and the physical addresses, physical locations.
So scrambling information about the memory is a kind of a key, kunji, जैसे कहते हैं ना, it's a key to identify where the physical or what is the physical location of a logical address. Are you with me? I have a logical address. I said I want to write to address location 1010. In my understanding, I understand that this address is equivalent to uh, binary number 10 or regular number 10. That 10 is represented as 1010. I want to write to address location 10. In a memory, there are 1000 memory locations. This 10 can be anywhere. How does it matter? What matters is where did I store my data and am I picking it up from the same place or not? Let us go back to the same bank example where we have a locker room. Have you visited a locker room? How many of you have visited a locker room? Not exactly a bank. It could also be in your swimming pool. उसके बाहर एक locker room होता है. Locker room तो कहीं भी होते हैं. हाँ? So others have not even seen a locker room. How many have not seen a locker room ever? Not seen a locker room even in a sports facility. Bank छोड़ो. Sports facility locker room you have seen. Okay. Let us say आप मंदिर या गुरुद्वारे जाते हो, वो आपके जूते लेते हैं तो आपको एक टोकन देते हैं. That is also a locker room in a way, is it not? मंदिर गुरुद्वारे को तो गए होगे कभी ना कभी. हाँ, कभी तो अपने जूते कहीं टोकन देके रखवाए होंगे. That is what we are talking as a locker room. Okay. So what do we say? Suppose you went to the temple or you went to this place and you deposited your shoes, you got a token. Now, while you were praying, please, please, whatever you were praying, there was cleaning happening in this particular shoe facility. Okay. And they moved one almirah from here to another or somewhere, whatever they did. You still have the token with you. You say, I want something from token number 95, because that is what you have. So now, since the almirahs have moved, Will going to the same physical location help you? Will they be able to retrieve your shoes from the same physical location? No. But now, do you need to know? Do you need to know where that 95 is? No. As a system designer, you only give one address. You only say read from 1010. Wherever the hell memory moved it inside itself, does it matter to you? No. Until the time you deposited your shoes, you gave the token and you got your shoes back, are you even bothered what happened inside the shoe factory or shoe house, whatever? No, you're not bothered. But the moment you gave your token, you were expecting shoes, your fancy bellies that you had deposited back, but you got dirty sneakers, hmm, smelly sneakers with socks. Someone had not even taken a bath for 5 days. The moment you get such shoes back, what do you do? Now you are interested. Now you are interested to know where did that 95 location go? Are you with me? So till that time, everything is working fine. Scrambling information you're not bothered about. But the moment something goes wrong, the moment something goes wrong, now you're very interested to see what happened. Where were my shoes placed? Could they have fallen down the rack? Could someone else's shoes have come here in my block? Anything could have happened. Now you are interested to see all that, is it not? So now, just logical location you're not interested in. You also want to understand what is the physical location. And that is the information that is made available to you when you have scrambling related information of the memory. It tells you where were the two adjacent words, two adjacent logically. So logically they were adjacent, 1010 and 1011. Logically they are adjacent. But practically it might have happened that जो मेरा पहला rack था उसमें 10 ही locations थी. So the second rack was on the left corner. So instead of right, the person actually has to go to left. Are you with me? So now when they have to retrieve the shoes, the person needs to remember that, okay, it was there, not here. If something has gone wrong, I don't need to look at the left corner. I need to look at the right corner, or wherever that particular rack is. Is it not? So that is why scrambling information is important. How you use the address bits to physically place your words inside the memory is what scrambling information talks about. Is this clear? You might use some address bits as column decoding. You might use some other address bits as row decoding. You might use some other address bits as page decoding, and that will exactly define which rack or which section of my locker room, which rack, which row, which column. And the moment you say, okay, no, this bit goes there, okay, the rack changes. Are you with me? Or maybe just the column changes. But how you will retrieve the information, from where you will retrieve the information, definitely changes. So one of the very key verifications that you have to do as a memory designer is that I wrote to location 1010. When I read, am I getting the right data back? This verification is not done at a, what do you say, a typical schematic level, but this verification is done after the LGS has been cleaned. So your layout is ready. And after the layout is ready, means the physical locations of every bit are now established. This verification is done at that point of time. Is it okay? Yes, that is a physical verification that we do after the physical instance is available to you. Okay. So that's a verification of the scrambling information. because if there is any failure on silicon, you need to recover from there. Okay. Then we went into the case of architectural choices. We said that the number of pre-decoders that we choose, the number of post-decoders that we choose, how we do the pre-decoding, whether there are 2 to 4 pre-decoders or 3 to 8 pre-decoders, how many of them are there, uh, whether this pre-decoding is dynamic or static, NAND based or NOR based, all these design decisions have a very strong bearing on your memory's PPA. Because if, for example, you choose to use NOR gates, then only one word line is to be selected according to the NOR gate methodology. Remaining all the gates will discharge. There is a large amount of power consumption that is going to happen. But NOR designs are, by the virtue of having a very small stack, also always faster than NAND type of designs. So while the power has increased, the performance has improved. Are you with me? Similarly, there could be an impact on area. If you choose multiple 3 to 8 decoders in the beginning versus multiple 2 to 4 decoders in the pre-decoding stage, then if you have, let us say, 8 or 12 address lines, it could lead to a very different number of post-decoded lines that you have to route. And that could be an area penalty. We also discussed about the fact, because someone asked this question, about how big my NMOS stack can be. And we saw that if you keep a very large stack, let us say more than 4, then the performance degrades abruptly and very badly at low voltages. So we try to keep the stack within 4. What this may mean is that we are decoding the addresses in multiple stages. Already we were talking about pre-decoding and post-decoding, but if the stack height has to be maintained to be low, then there may be an additional stage that could happen either at pre-decoding stage or at post-decoding level. Are you with me? How many of you have actually watched the relevant video after the class? It's been 4 days, 5 days after the class. How many of you have watched the video after the class? Either the video that is a recording of this live session or the same video that you have in your Cognitrix app. Okay. So how many of you had already watched it before coming to the class? Okay. So then is it fair to assume that you have watched the video and at least either before the class happened or after the class happened and it is stable for you? Is it okay? Any questions?
I had a question regarding the so
No, no, पहले एक बार इससे. Any questions related to the architectural choices and address decoding that we have discussed until now? Mhm. Yes. So scrambling information is to enable debug, is to enable good test results, to identify where the failure is happening and get a handle on what is the cause of failure so that you can prevent the failure from repeating. So we had talked about that in the last class also, and we can repeat that again. So for banks, we said that in this class, we will use one particular lexicon, we will use one particular nomenclature, but always realize that whichever company you join or whichever, so language we agreed is a conspiracy, is it not? Language is a conspiracy between people. We agree upon calling something something, okay? And we're talking about a conspiracy that we're using in this class. That doesn't mean this is to be used everywhere or may not be used everywhere, okay? So let us say I have this memory array, and in this array, I have multiple local bit lines that connect to the global bit line. In this class, we are calling this as a bank, which handles one local bit line. Okay. And if it is a very large memory, I may have multiple of such arrays placed next to each other for various reasons, including managing the aspect ratio. This is being called as a page. Okay. Now, let us say you gave some address. You gave, uh, let us say you have a 15-bit address bus, and you use the lowest bits, LSBs, to determine which page my location would go to. Okay. LSBs. So what will happen? Your word 0 will be here. Your word 1 will be here. Your word 2 will be here. So your logically adjacent words would be placed not just in different banks, but on different pages altogether. Because you use the LSB to tell which page is to be selected. Are you with me? यहाँ तक clear है? Now suppose you had chosen the LSB to select the bank. Then what would happen? Then word 0, word 1, word 2, word 3, word 4, word 5. That is how it will move. Because LSB is selecting the bank. With me? Now suppose you said my LSB is used to select the column address bits. Then what would happen? Then what we have already seen earlier, word 0, word 1, word 2, word 3, they will be adjacent to each other physically also in the number of mux that you have. If the mux is 4, then word 0 to word 3 will be together, and word 4 will go to the next row. Are you with me? So there is no single formula of कि पेज के लिए ये वाली बिट्स यूज होनी है. आप जैसा यूज करोगे उसके बेसिस पे स्क्रैम्बलिंग चेंज होगी. Now you like that scrambling, you do not like that scrambling, that is your choice. You have an agenda, you want all the adjacent words to be on the same page. You would use LSBs on column decoding. You want all the adjacent words to be on different pages for whatever reason. You would want LSBs to be on page selection. Are you with me? What I'm telling you is, whatever you use, update the scrambling tables accordingly. If you're smart, you can use bits, address bits in such a way that, for example, if I say I'm using LSBs for column decoding, then I also know that, okay, at a time I will need a burst of 20 words, 24 words, and I'm using LSB, so column decoding. Then all these 24 words are going to be on this page. So the remaining pages I can put into standby. I can reduce leakage power. But if you wanted speed or if you wanted something else, a burst mode operation, you could say that, okay, I will keep word 0 here, word 1 here, word 2 here, word 3 here, word 4 here. So that while this resets, I'm already accessing this next one. After I access this one, I'm already prepared to access the third one, and so on. So it depends on what your target is. As we'll go into DRAM, we'll talk about bit interleaving and interleaved methods of accessing the memory to improve the throughput. So कोई भी ये नहीं है कि यही अच्छा है या वो अच्छा है. As a designer, what you need, as a designer, what you need, that is what you should do.
There could be a reason between a crosstalk and or
Yes, as a designer, if you feel that these should not be together, you choose the address bits in a way that they are not physically together. So it is a designer's decision. Do not leave it to chance. You are empowered to choose the overall uh, PPA of your memory carefully. You better utilize that lever that you have.
then there would be a trade-off between this leakage and
That you have to see. See, any design decision will lead to some trade-off. Whatever trade-off comes, you have to evaluate it. You have to see if it is acceptable to you or not. Is it okay? Sorry? See, what we just talked about was that if you have implemented Mux, then bit interleaving is here. It is independent. Whether you're talking about a page or a bank or something, you've done bit interleaving, you've done bit interleaving. Which address bits you use for decoding the Mux will decide which words will sit next to each other. That is all I'm saying. Is it okay? It's something like on a particular, you have a living complex, a housing complex, or let us say you have gone to a dormitory, entire batch has gone to Kullu Manali for a picnic, and there's a big dormitory. Every room has 4 beds, or every room has 2 beds. That is the mux. 4 beds mean 4 people can sit together. 2 beds mean 2 people can stay in the same room. Now, how you distribute who goes where, alphabetically, height wise, age wise, how the hell does it matter? Bit interleaving is there are rooms with 4 beds. Now you decided, oh, A, all 4 A's go to room 1. Fine. You say, no, A, then B, then D, then F. You choose. That is about how you're using address bits for decoding. Bit interleaving is entirely different. It's independent. It only your decoding style chooses which ones will go into the same room. That's it. That is scrambling. Is it okay?
I have it down with the NAND and NOR artics. So are we using this in the pre-decoding or post-decoding?
Wherever you choose, you have this option everywhere.
The figure that you've shown this way, we using both NAND and NOR, like the pre. So,
At every see, when you are designing the pre-decoder, do you not have a choice to choose between NAND and NOR? There also you have a choice.
I'm using NAND, then pre and post both will be NAND.
No, not necessary. See, it is only about bubble shifting, na? In that first course on bubble shifting on these digital circuits or whichever, digital circuits was the course where you did bubble shifting. You only need to say, okay, now this NAND I want to convert into NOR. You already played all these games. So that is what we will do. You choose based on what is the PPA that you want your memory to have. What we finally want is I should be able to reach a particular location and then retrieve, first store and then retrieve from that location. You do buffer shifting to achieve whatever other design parameters and design results you want.
Nor help increase the power. Like,
So do a simulation, see, analyze. कुछ तो खुद भी analyze करो. I'm telling you it increases power. Analyze and see. Then check with me in the office hours, confirm with me in the office hours if you're not able to see the. Is it okay?
पूरे बार का लॉजिकल एफर्ट्स निकालेंगे फिर पूरे बार का लॉजिकल एफर्ट्स निकालेंगे फिर कॉम्बिनेशन देखेंगे जिसमें डिले करना.
Yes, you have to look at the logical. We discussed about logical effort and sizing of address decoding in the last class also. So you apply the logical effort method, identify what is the sizing that you would want to keep. You will automatically arrive at what is the PPA that you are able to achieve. Is it okay? So see, this is an advanced course. You can't be spoon fed. Play, do these experiments and find out for yourself. I was very surprised with the right driver discussion that we just had. We should not have needed that discussion in the first place. That extension I was assuming you guys would do. It was just a coincidence that I asked that question to you. I could have directly asked that question in the mid-sem exam. Then what would you do? Sir, आपने क्लास में न्यूमेरिकल नहीं कराया. Are you little children today? Whatever we are discussing, there is a mathematical, uh, consequence of that choice. You have to just extend that learning. Is it okay? See, most of you within next 1 year, you will be either in an internship or in a job. If you will continue to think that your managers are going to feed you information and then you are just going to act on it like a robot, you are grossly mistaken. They will just tell you this is to be done, do. I'm just preparing you that you are able to do it. I'm here to mentor you if you do it wrong. But if you don't do it, you will do it for the first time when you do join your jobs. And this is not just about this course, any job that you join. See, this is one thing that you should always keep in mind. In triple IT, as of now, you are at the status of a student. You are a customer. Hmm? You can demand that give me more numericals to practice. I will give you. We have this question bank that will be made available. You can demand this. At the end of DVD, you demanded, no. Quiz should not be on Saturday. Let's have it on a weekday. Okay, demand done. Do not assume that we have studied the lectures, go to every slide and explain that slide afresh. Demand met. Why? You are the customers. You are paying for my salary somewhere. You are the masters here. But the moment you join an internship or a job, you are a slave. Be aware of this. Not a slave in terms of a slave, but the fact is your status has now changed from one who gives the money to someone who gets the money. From a customer, you transition into the role of a vendor. And if you do not render your services well, vendors are changed. So while you are still customers, I'm trying to help you transition into the role of a vendor also. Not by not giving you information, but by nudging you, pushing you to become more and more independent. The choice lies with you. Do not think people are going to come to your table and teach you how things have to be done. अरे 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 नोना नोना बच्चा, तुम तो अभी अभी कॉलेज से आए हो, तुम्हें तो पता नहीं है यहाँ पे काम कैसे होता है, चलो देखो तुम्हें ऐसे सिखाते हैं. Nothing of that sort is going to happen. In most of the companies, you will directly be thrown into the workplace. In some others, you will be given some manuals, पढ़ लो and आगे बढ़ो. And in some others, probably you will be given some short 1 week induction training. How many of you have had some job experience until now or an internship experience until now? So, how was it? Were there people coming and teaching you, please, देखो ऐसे होता है, अब इसको ऐसा करो? How was it? Ria, how was it for you, your internship experience or whatever? Did they teach you how to write that Python script? Did anyone come to you and tell you कि इसको इस तरह से करना है? If you had said no, even then, they would have just given you some work and gone away, is it not? That must have happened with many of your colleagues. Whether you do or not do, that's okay. Interns, you're hardly a liability. You're more of a liability than an employee, okay? But the moment you join as an employee, somewhere here, people had raised hands.
They're already full timers doing that job more reliably. So you have to approach the manager to get some work. And they will sign it. They will give you a deadline. They don't help you with what to do exactly. So you're supposed to do that jobs. And
So you told a job and you have to complete it by on your own.
you won't get online resources or anything like that.
Yes, no chat GPT there. Access is restricted because everything that you will be working on is company confidential. So you better prepare yourself well. And ये तो भी internship का experience है. Job का experience अलग ही है. Are you with me? So please try to analyze whatever you are asking first and then ask. If you join a job and you flood people around you with a lot of questions, the seniors will, start to evade you. नहीं नहीं वो आ रहा है भाग लो यहाँ से. Why? Because I have 10 hours of work pending on my desk. This guy will come and start asking me so many questions. Now, that doesn't mean I don't want you to ask questions here. I really want you to ask questions. I encourage you to ask questions. Abhi tak, it's almost 50 minutes. I've not even started anything new. I want you to ask questions here. But I'm telling you that if you are not judicious in what you ask, you will earn a bad reputation for yourself in your jobs. You have to be very discerning. You have to do your homework first before you put forth any question there. Over here, it is different. Yes, I want you to ask. But I want you to gradually move into a zone where you have done some analysis yourself first and then ask. That is why I insist. Watch the videos first. Or even when I'm doing the revision here, I today asked, how many of you watched even the lecture that we recorded and then shared online? So that you start to apply your brain independently, independent of just being in the class. When you're doing a course, you're not spending just 3 hours in the class and done. We're expecting you to spend at least 10 hours every week on the course. And during the project, it will be definitely much more than that. खाली class में learning नहीं होना है. You have to put an effort after and before the class to get the learning there. Are you with me? Okay. Now coming to, so we have understood about NAND decoding, NOR decoding, all of that. You watched the video once earlier. You watched the video later also. Oh yes, you had a question on the quiz. Yes.
There was this question on quiz that tighter equalization tolerance always reduces as rate access. That's what was a false question. So this is marked as false.
Yes.
Because My understanding was if you have a tighter equalization tolerance, so the cycle time would increase and your read access time should decrease.
uh, उसमें एक्सेस टाइम लिखा है, मेमोरी टाइमिंग्स लिखा है.
Read access time.
Okay. So if you have a tighter tolerance for equalization, then the overall offset requirement that your bit cell has to create will reduce. In that context, then the read access time would reduce, but the overall memory timings would degrade. So this can be corrected.
The, what? Yes, sir. And also there was this. Yes, sir. This one. There was this question on why is separate recharge used for maintenance and amplifiers. So one of the reasons that has been marked as correct is to get memory reset at the same time.
Yes.
So what is meant by this?
So if you were to uh, if you were to recharge both sense amplifier and bit lines at the same time, after sense amplifier has acted, my memory reset would happen very, very slow. But if I separate the two precharges, I can start to precharge the bit line much earlier. It is a much bigger capacitance and it will precharge soon. But even though you are starting to precharge the sense amplifier later, because the capacitance is less, it will match that and it will precharge at the same time. So that is how you have to design it, that they actually converge at the same time.
No, one more question that I just had. If we use a negative right acid circuit, so our mean that precharge will also become a little bit slower, right? Because I have to trigger. So the cycle time will kind of degrade when we use a negative.
Yes, many things will change when you use a negative bitline circuit. So you're already operating at a low voltage. That is why you needed negative bitline. So timing degradation is anyways going to happen. But the fact also remains that negative bitline will result in a faster write time inside the memory cell. So that would also help you recover something. So it's no one thing that you can say about a memory, Madhav. You have to really play with the memory, play with these design techniques, and then you will be able to arrive at, okay, what is my final PPA? So do not, in memory design, do not consider everything, anything, in fact, as sacrosanct, except that area is diamond. Area is diamond, area is diamond, area is diamond. This is the baseline. Everything else you do, you have to evaluate. Is that okay? So, हमने, we looked at those NAND gates and we looked at those NOR gates and we looked at the way these dots were placed in your crossbar. But those dots mean nothing. Those dots may mean something to you in a schematic, but they mean nothing on the layout. So how is this done in layout? Because finally, whatever you do, it has to be implemented. So how does this NAND programming, that inputs of this NAND are going to be equivalent to 0101, and the next NAND are going to be 0111 or 0110? How are these inputs programmed?
Using device programmation.
So Madhav is saying using device programmation. What do you mean by device programmation?
So when you want two lines to suppose you have two lines and you want them to get connected with when a particular input and one, so you have an NMOS with whose gate is connected with the input and need to connect lines.
Okay. So what he is saying is that if you have an NMOS that needs to connect to one particular line, so you place the NMOS there. And then what happens? You see, what have I done? I said, okay, the topmost is A2 bar, A3 bar. That is the same thing that is going to four devices, four adjacent rows. That is the same connection that is going. Then A2 bar, A2A, A3 bar, that is going to the next 4, and so on. So what you could do is you could just place the devices where you want the programmation. And I have not shown metal ones and metal twos over here, but you do realize that finally this has to be a NAND gate. A NAND gate which connects the PMOS over here and the NMOS is on the other side to be able to generate the word line. You want to see the previous slide again? I can show you the previous slide again. So what we were saying was that there is a NAND gate, there is this clock signal on this side, precharge on this side, two devices, there's something going on that side. So all this has to finally fall in place. Are you with me? So there is a lot of metal one that you will need to route to connect these transistors, which you have presently just placed randomly according to the programmation. So while it appears that आपको बस एक device को कहीं कहीं place करना है, realize that there is a lot of metal 1, metal 2 jugglery that you will have to do alongside placing these devices like this. That is undesirable. That is undesirable also because of one more fact, which we call as envelope proximity effect. In advanced technologies, the envelope boundary results in some scattering of dopants close to the boundary. That changes the VT of devices that are closer to it. So what would happen is that uh, this set of rows, which represent 9, 10, 11, and then 12, 13, 14, 15, where the NMOSs will be far closer to the N-well boundary, will behave differently. Their selection and deselection will happen differently than, let us say, word line 0, 1, 2, 3, because their NMOS is farther away. Okay. So we already know that mismatch is going to cause us trouble. We do not want additional sources of mismatch. So what do? We actually put all of them together. And what we then do is we just change the programmation through VRs. Are you able to see this? This is the same circuit now implemented by while taking care of N-well proximity effect. And the programmation is happening just by changing the place where my VR will be located. Are you able to see this? So as a memory layout designer or as a software designer, the software, like the memory compiler software part, where you have to tile various row decoders and IOs and everything together. As that kind of a designer, you will need to see where these programmation dots will come. This is a part of the software that is written at the memory compiler level. Are you with me? Any questions around this?
Well, when we do here programmation, it will be the number of layers we are using in the
So you anyways need metal 2 to route your pre-decoded address lines.
device program.
Yes. Otherwise, how will that information go up there? Metal 1 is there for local connects. Only in metal 2 you can bring. I'm just saying that for metal 2, you just change the via, the location of where the via is come dropped. Okay. So what is Envel proximate effect? Who will explain?
Get bounced or decoderless, and some portion of the transistor have more amps than required. What happens is the transistor that goes to the well, they have different electrical characteristics than the transistor which are far away from the.
Thank you. So, DVD first lecture, second lecture, we talked about how transistors are designed, manufactured. याद है? सर कहाँ इतने सालों पुरानी बात कर रहे हो? इंटरव्यू में पूछा जा सकता है, अच्छा तो याद कर लो. So, suppose over here I have to make a P well or an N well. Let us say जो भी कुछ भी एक हमें बनाना है. Okay. What do I need to do? I need to do some doping in that region. So I will need to create a mask where when the ions are projected from the top, they don't touch the silicon over here. I'll have to create some mask. है ना? यहाँ पे कुछ oxide रहेगा या कुछ भी रहेगा, something which will not let ions that are being implanted to enter into my substrate region. At the other time, I will just replace this and I will have the mask on the other side and I will dope the other side. But I need these masks. Now, the important thing to realize is that how much ever vertical you want to create these masks to be, finally they will have some slope. And when you throw ions vertically on the slope, they get reflected. Physics that you had studied, conservation of momentum, deflection, everything is going to happen. And notice that near the boundary of the N well, this was your mask. So near the boundary of the N well, there is going to be a region where there are going to be more dopants. So what happens to this particular device, which is very close to the N well boundary? It has a different VT than the devices far away. This is what is called as N well proximity effect. A different VT means that we are going to also experience different currents, different capacitances. So many things are going to change. So this is what is called as N well proximity effect. This leads to variation in the delays for, let us say, word line selection. Now we want to start mismatch, and you know that mismatch is already a problem for SRAMs. We saw those 60 cells and we saw that if the sigma variations are 3 sigma, then there is this kind of impact on stability, this kind of an impact on writability. If it is 4.5 sigma, things simply go for into a different range altogether, and so on. So you already are struggling with mismatch. You do not want any additional source of variations into your system. That is why, as much as possible, you will try to avoid N well proximity effects to impact any additional delays in your system. Are you with me? Is this clear? Any more questions? मतलब? So you tell me, you know the formula of VT? What happens when the Na, that is the dopant concentration, changes in the substrate? I would say simply, you know that the doping concentration is going to increase. If you simply put that in the VT formula, can you not deduce whether the VT is going to increase or reduce? Whatever, I'm not giving you the answer. I want you to find out for yourself what will happen. Is it okay? Can I leave it like that? I've already established with you that VT will change. For me, in this class, that much is sufficient. You want to find out whether VT will increase or reduce. Find out. Okay. Is it okay? So we'll now start with mismatch. And for this, we will use a tutorial that was given in one of the very old earlier DACs. How many of you have watched this video already? So I would suggest all of you watch this video, whether I have covered this in the class yet or not, because it's a very, very interesting set of slides that were presented in that tutorial in DAC. Okay. And the slides will also be made available on the Google Classroom. You can watch the entire deck of slides. I will only cover a few of them in the class. Because as a memory designer, you really need to get a very good handle on understanding what is mismatch and what are the various sources of mismatch. Because only when you understand what are the various sources of mismatch can you do something about it. So that's a very important chapter that we have in this particular course. So you better uh, be prepared before the next class when we will discuss this in the class again with all your questions that you may have. Is that okay? One thing that I want to establish with all of us is that there are two kinds of mismatches. One are systematic mismatches. For example, anvil proximity effect is a systematic mismatch. You can model it. He asked me, what is the what how will the VT change? You can easily model it. आपके पास VT का equation है which includes Na as a part of it. Is it not? In the VT equation, Na is one of the variables there. You just put what happens if Na increases, what happens if Na reduces, and you will have the answer for yourself. Is it not? So these are variations, or the impact of these variations can actually be modeled based on where your device is placed. Stack effect. What is its impact? Can be modeled. So there are some kind of variations which can be easily modeled. Those are referred to as systematic variations. There are others which you have no control over. For example, two devices placed next to each other, proximity is exactly the same, common centroid you did, everything you did. Even then, there is going to be some variation that will come in their behavior. This cannot be preempted. This cannot be taken care of by design. This is the nature of any manufacturing process. This is called as random variations or random mismatches. And uh, this, the margin related to these random mismatches, you simply cannot do away with. You have to ensure that these mismatches are very well margined into your design. That your design should not fail in the presence of these random variations. It is for this that you have to do Monte Carlo, not for estimating power. Is it okay? Okay, we will stop here and we will start with mismatch in the next class. And it is best if you come prepared with what mismatch is and with all your questions on mismatch. Okay? All the best.